Greetings and welcome to the Exam 1 review for Chemistry 221. In this review, what we'll do is we'll emulate what we would do in a normal lecture. And in a normal lecture over 1 or more hour periods, I would present some questions. I would give the students time to work on the question before actually answering the question. So it's a way to kind of check your work and see how you're doing. In this video, I would encourage you to do something similar. I'll show a question. I'll then point out a time where I would recommend pausing the video, so actually hit pause on the video. You can then work on the problem, and when you're ready, you can unpause it, and then shortly after that, I will start talking about it. So this is for you, definitely to let you know how you're doing with material and stuff like that. And if you do run into something which is very strange, then let me know. I am here to help, absolutely. You can also talk to the Learning Success Center, Avid Center, people like that. They are there to help you too, but we want you all to succeed on this midterm, and it's definitely stuff you can do. So probably what's going to happen for the first midterm, and you should double check with me because things might have changed since the time I made this video to where you're looking at it right now. But in a normal midterm, the exam will be over chapters 1, 2, and 3. So chapters 1 and 2 were kind of introduction chapters. Chapter 2 introduces the atom. We talked about the periodic table, stuff like that. And then chapter 3 is how light and chemistry get along. We talk about the quantum numbers, talk about nomenclature, lots of things like that. When you come to the midterm, you should definitely bring your calculator. Pencil or something to write with would be cool. The nomenclature lab will be due, so make sure you have that ready to turn in. There'll also be the exam prep worksheet 1 to turn in. Exam prep worksheets are basically some questions where the answer is given. You need to show your work how you go from the question to the answer. In addition, also bring the identification of an unknown compound lab, the printed lab. We will have a lab afterwards. Your goggles will be cool for that lab, so I would encourage you to bring those along as well. If you have those things, you'll be good to go. Now, the midterm itself should have, at least at the time of me making this video, 12 multiple choice questions, 4 short answer questions, and it should be about 90 minutes in length. The exam is closed notes, so you won't have notes or the book or anything like that next to you. You will be able to use a periodic table, which I will provide for you, and it should be pretty chill. And then you'll take the midterm, and then the next time I see you, like the following lab period, I will return the midterm to you with a summary sheet that says how you're doing in the class as of this time. And I would encourage you to check that out because sometimes it's true, I do make mistakes. I want you to have the grades recorded that you actually got, so double check that. But also if there's a lab missing, this will be a good reminder to turn those in, which is kind of important. So good luck with your studying. Okay, again, if you have questions on anything, contact me. I'm more than happy to help. But with that being said, let's start the exam review and see what this midterm will be all about. In this question, we have a piece of metal with a mass of 33.2 grams, and we place it in 10 milliliters of water in a graduated cylinder. And you can see in the little picture there, there's kind of a before and after picture of what's going on. So notice on the left side, or in the middle, I guess, it says 10, that's where the water goes up to, 10.0 centimeters cubed. And after putting the metal in, the water level rises to 22.3 centimeters cubed. Using all this information, determine the identity of the metal. And you can see a list there of different metals and their densities. So really what I'm asking you to do here is find the density of the metal, and then you can compare the density to the one that's closest in that list to find the identity. So see if you can do that. So at this point, pause the video, and when you're ready, then you can unpause and start up again. Okay, I'm going to assume that you now have the problem done and you're ready to talk about the answer. And again, if you haven't done the problem yet, again, I encourage you to pause it, work on it, and then see how you did. But anyway, if you are ready to rock and roll on this one, this is a density problem, all right? And density is mass over volume. The mass is usually represented in grams, and volume can be in milliliters or centimeters cubed. Milliliter is equal to a centimeter cubed, so there interchangeable. Now, the volume that the metal takes up can be found by the difference of the water volumes. So you can see the water started at 10.0, it went up to 22.3. So 22.3 minus 10, or about 12.3 centimeters cubed, that's going to be the volume. That's going to go in the bottom of your calculation. And in the top part, you want to put the mass of the metal that caused that volume displacement. That's the 33.2 gram number. So in this calculator then, 33.2 grams divided by parentheses, 22.3 minus 10, parentheses, or just, of course, 12.3, and you should come out to answer E, about 2.70 grams per centimeter cubed. And if you called it 2.70 grams per milliliter, that's fine. A centimeter cubed and a milliliter interchangeable, no big deal. Cool. Here are some temperatures that you can find on different places on the Earth. 29 degrees Celsius, 45 degrees Fahrenheit, and 256 Kelvin. And I'd like you to put these three temperatures in order of increasing temperature. So the coldest first and the warmest, the hottest one would be last. And so what this question is asking you to do is basically convert the different temperatures into a common unit. Now remember that to go from Kelvin to Celsius, Kelvin values are never negative, but Celsius values can be. So what I would do on this problem is convert Kelvin to Celsius. I would take 256, subtract the 273.15 number, and that's going to be that value in Celsius. So you can convert 256 Kelvin to Celsius. Then I would do the same thing with Fahrenheit. Now Fahrenheit, the temperature in Fahrenheit equals 1.8 times the Celsius temperature plus 32. So to get the Celsius temperature by itself, you would first take the Fahrenheit value and subtract 32, and then whatever's left over, you would divide by 1.8. So see if you can do this on your own first. And again, this is going to be a good place to pause the video. And when you're ready, you can unpause and we'll talk about the answer. I'm going to assume you have worked on the answer and you're ready to see how you did, and that's totally cool. The game plan in this is I would convert Fahrenheit to Celsius and Kelvin to Celsius. If you wish to convert everything to Kelvin, that's fine too, or everything to Fahrenheit, but Celsius is kind of the intermediate part. That's just my recommendation. Now, 273 Kelvin is 0 Celsius, and that temperature is lower than 273. That's pretty cold. All right, so 256 sounds like that's going to be the coldest. On the other hand, 45 degrees Fahrenheit. Now, if you grew up in Oregon, where we use Fahrenheit all the time, 32 Fahrenheit is freezing. That's where water freezes. And so 45 isn't too high above that. So I think that 29 Celsius, that sounds pretty warm to me. So you can sometimes use just kind of general explanations here for what's going on. Of course, the best way would be to solve it. So let's look at this. The answer, by the way, is D, and the Kelvin temperature is the coldest in that list, followed by Fahrenheit and followed by Celsius. But here you can actually see the values converted. So this first part right here, we're taking the Kelvin temperature, 256, and subtracting 273.15, cut it off at the ones spot. That's this sig fig thing to do. So you get negative 17 degrees Celsius, and that is certainly colder than 29, so that's a good number to have. Now we need to convert the Fahrenheit into Celsius as well. So you can see here's the Fahrenheit temperature. You subtract 32 first, then you divide by 1.8 or 9/5, either way. Anyway, that temperature comes out to be 7.2 Celsius. So it's warmer than the Kelvin's negative 17 Celsius, but certainly less than the 29. So that's why answer D would make the most sense here. This question is about length and metrics. All right, we've got 4 lengths here: 215 millimeters, 9 centimeters, 2.3 meters, and 0.125 meters. And it says put these in order of increasing size. So smallest to largest is what you want to do. Now, there's a whole bunch of different ways to solve this problem. I would probably convert things to meters. You already have 2 meter values. So if you can convert 215 millimeters to meters and 9 centimeters to meters, that would be, I think, the less work. Of course, you have to know about the metric prefixes. So milli is 10 to the minus 3. So that means that a millimeter is 10 to the minus 3 meters. Alternatively, of course, you could use 1,000 millimeters equals 1 meter. Either way is fine. Now, centa, C there, centa is 10 to the minus 2. So a centimeter is 10 to the minus 2 meters. You could also use 100 centimeters per meter. But either way, see if you can convert those over, put them from smallest to largest. This is a good place to pause the video, and when you're ready, unpause it and we'll look at the answer. Okay, I'm assuming at this point you want to look at the answers to this question, and that's fantastic. Again, the punchline here is put them from smallest to largest. And I would put things in meters, all right, because you've already got 2 of them meters. You only have to convert 2 of them, but you can convert them all to any unit you want to. Going from millimeters to meters, you want to basically divide by 1,000 or multiply by 10 to the minus 3, either way. But you want to move the decimal point 3 positions to the left. So 215 millimeters becomes 0.215 meters. And you can see that that is bigger than 0.125 meters, but not as big as 2.3 meters. 9 centimeters, you want to divide by 100. There are 100 centimeters per meter, and that will tell you the number of meters. So dividing by 100 means essentially moving the decimal 2 to the left, 0.09. So in this problem, 0.09 meters or 9 centimeters is the smallest, all right? Then 0.125 meters is the next biggest one. Then 0.215 meters or 215 millimeters is next, followed by 2.3 meters. So this is a great question just to kind of check yourself, see how you're doing with those metric prefixes. In chemistry, remember, the centa and milli are 2 of the 5 really important metric prefixes you need to know. The other 3 are kilo, micro, and nano, and we'll see all of those throughout the course. Kilo is 10 to the 3, micro 10 to the minus 6, and nano 10 to the minus 9. Which statement below describes the composition of a neutral atom of iron 58? In this question, you can see there's neutrons, protons, and electrons, and the first 4 answers. And I want to test your knowledge of what it means to be neutral and also what that dash 58 means after the iron. So try this problem out, pause the video, and when you're ready, just unpause it and we'll talk about the answer. I'm going to assume at this point that you have worked on this question and you've got an answer, so let's see how you did. The first part of this question says we have a neutral atom, and a neutral atom can only happen when the protons and electrons are equal to each other. So if you look at these particular answers then, 2 of them right away are not going to happen, all right? In A, you have 32 protons and 26 electrons. There are more protons in A than there are electrons. That, whatever A is, that's going to be very, very positive. More protons and electrons means positive. So answer A is not going to happen. The other one that's not going to be neutral is C. If you look, that one has 32 electrons, 26 protons. That has more electrons than protons. That's going to be a negative ion. That one's not going to be neutral either. So our answers here are either going to be B or D or possibly E, and I'll be honest, honest, it's not going to be E. So let's think about now what the iron 58 part means. Iron on the periodic table is number 26. And like we talked about earlier, 26 is the atomic number. And the atomic number represents the number of protons. So in both B and D, there are 26 protons. Those are both going to be iron atoms and stuff because they've got protons. And because B and D both have 26 electrons, not only are they iron, but they're going to be neutral. So the last thing we need to do then is think about what the 58 means right there. 58 is the mass number, and it equals the protons plus the neutrons. So we have to figure out a combination then of protons and neutrons in B and D, which are going to be equal to 58. And 26 plus 26 on answer D, I think, is 52. So I'm going to think then that the answer is B. And it is 26 protons plus 32 neutrons is 58, all right? And that's where the 58 comes from. So if you have a neutral atom of iron 58, you're going to first of all have equal protons and electrons. Iron always has 26 protons, so that means 26 electrons as well. And then finally, the 58, to figure out the number of neutrons, you would go 58 minus 26. And that's where answer E comes in. So we have enough information to answer this question. Absolutely, it's answer number B. Cool. An element E has several naturally occurring isotopes with the following abundances. So we're just listing them as some random capital E. All right, don't worry about that. But notice there that 72E is about 54.5%, 73E is about 15.6%, and 74E about 29.9%. And the question then says, the most reasonable atomic weight for this element would be, and it lists 5 possibilities. So see if you can think about what the percentages mean when coupled with their mass number, and how those two go together to find the atomic weight, which is essentially an average of all the masses of the different isotopes. So this is a good place to pause your video, try this problem on your own, and then in a little bit we'll start up again. Okay, I'm going to assume that you've worked on this question and you've got an answer. You want to check it out, and let's do it. When it comes to isotopes, all right, sometimes one isotope is more abundant than the other. And if you look at those 3 isotopes listed, the 72E, that's more than half of all the different isotopes. That's more than 50%. So the atomic weight is just an average of all of them. And because 72 is more than half, that means that the atomic weight, the average, will be somewhat close to 72. All right? It's not like it's 90% 72, but it is more than half. So the atomic weight, the average, will definitely sway more towards 72. But you do have an appreciable amount of both 73 and 74. All right, it's not halfway up, but it is quite a bit. So having an answer of 72.1 in A is probably a little too enthusiastic. Like if we had 90% 72 and maybe just a little bit of the others, that would make sense. But that's probably too much. On the other hand, 73.4 and the bigger ones below it, those would imply that you had high abundances for isotope 73 and 74. And they're just not that big compared to 72. So I would argue in this question that probably answer B is the right one. But wait, Dr. Russell, I want to do it a math way. I don't like your hand-waving ways. Oh, good. Whoever said that in the back of the classroom, this is a stupid thing I do sometimes in lecture. But anyway, babbling. If you don't like my hand-waving way, which is kind of what I was doing there, you can also do it the math way. And that's what this part is down here. Now, you can take the decimal version of those percentages. So 54.5 would become 0.545, and 15.6 6 would become 0.156. You take those decimal versions and you multiply them by their mass, all right? So 0.545 times 72, because that's the mass number of that isotope. And you do the same thing, 0.156 times the 73, the same thing, 0.299 times 74. Add those numbers together, and you end up getting to 3 sig fig 72.8, all right? So that's an alternative way to do that. So this kind of questions have two ways. If you think about what it means to be an average, you can a lot of times kind of work your way through it. But this math way works really, really good too. The symbol right there, which is a sigma, that just means add up all of them. And that means add up all of the abundance, that's what the decimal version of the percentage is, times the mass of that particular isotope. So like times 72 times 73. Either way works great. You work with the way that works better with your learning style. When the ion strontium 2+ forms, then there's 5 different statements, and one of those statements is correct and the other 4 are incorrect. See if you can figure out which of those statements is correct. Pause the video, and when you're ready to hear the answer, then unpause it and we'll talk about it. Okay, I'm assuming that you're ready to look at the answer, which is fantastic. Now, strontium is number 38 on the periodic table. It's a group 2 or group 2A metal, and those metals love to form positive 2. Now, strontium number 38 means that it has 38 protons, and 38 protons means then that a neutral strontium would have equal number of electrons, would have 38 electrons. So neutral strontium would have 38 protons and 38 electrons. And if you make a positive 2 ion, you are going from neutral strontium, just Sr, which is a metal, if you look on the periodic table, you're going to make strontium with a positive 2 charge, and those 2 electrons are kicked out. Now remember, in neutral strontium, 38 protons, 38 electrons, that's what neutrality is. If you lose 2 electrons, then you still have 38 positive 1 protons, but only 36 negative 1 electrons. So 38 minus 36 essentially is where the positive 2 comes from. Those 2 electrons are lost, more protons than electrons, that becomes a positive ion. So some of these here say something about 1 electron. That's not going to happen. If you have strontium, you're going to be losing 2 electrons. You're not losing 1 electron to make a positive 1 strontium, you're losing 2 of them. The last one, E, is also not right. If you lost 3 electrons, the strontium would have a positive 3 charge, and you certainly don't have that. So it comes down to C or D, and if you look carefully at both of those, one says loses and one says gains, all right? In this particular problem, strontium is definitely losing the electrons to become positive, all right? If strontium were to gain 2 electrons, then you'd go from 36 protons and 36 electrons to 36 protons and 38 electrons. And 36 times plus 1 plus 38 times negative 1, that would give you a negative 2 strontium ion. And that's not how that flies. So definitely the answer here is going to be C. It's losing 2 electrons, it's becoming positive, and it does have the same number of electrons as krypton. If you only have 36 electrons, that's the same number of electrons that neutral krypton would have. That'll be important for us later on. We'll talk more about that in a future lecture. How many emission lines are possible considering only the first 5 quantum levels of hydrogen shown below? This is basically a question about Bohr's model of the atom. And absorbance lines are when the transitions start at a lower N and they go to a higher N, i.e. an endothermic process. But emission lines, which is what we're looking at right now, emission lines are for starting at a higher N and going to a lower N. So see if you can use this information and the diagram that might be helpful there on the right and figure out how many possible emission lines there can be for the first 5 levels of hydrogen. So pause your video now. Okay, at this point, I'm going to assume that you have worked on this question and you want to see how you did. So without further ado, let's get into the answer. So as I said earlier, emission lines are electron level transitions where you start at a higher N and you go to a lower N. Now, all electrons start off at N equals 1. That's the closest place to the nucleus. And an absorbance line means you go from a lower N to a higher N. Absorbance lines are endothermic, all right? And that's why they arrows are getting bigger, lower to bigger. But these are emission lines. So as an example, let's say you had an electron starting up here at the N equals 5 level. Well, that electron, after a while, would maybe relax back down to the N equals 1 level. That would be exothermic. It went from a higher energy to a lower energy. That would be the releasing of energy. So the 5 to 1 transition is an emission line. But you could also have a 5 to 2. Doesn't have to go to 1 necessarily, right? You could have a 5 to 3 and a 5 to 4. So those are 4 emission lines right there. But you don't have to start at N equals 5. You could start at N equals 4. And N equals 4 to N equals 1 would be 1 transition. You could also have a 4 to 2 or a 4 to 3. So those are 4 from N equals 5, 3 from N equals 2. You could also have it start at N equals 3, N equals 3 to 1, or N equals 3 to 2. That's 2 more. And then finally, you could also have a 2 to 1 transition. So there's 4 in this initial group, 3 here, 2 here, 1 here, 4 plus 3 plus 2 plus 1, I believe that's 10. Now another way, instead of writing arrows, which is what I did in the diagram there, you could write 5 to 4, 5 to 3, 5 to 2, etc., etc. Those are alternative ways to represent the number of emission lines. But in the end, you should have 10 emission lines from the first 5 levels for hydrogen. You would also, of course, have 10 absorbance lines, but those arrows would be going up. They would be endothermic instead of the exothermic emission lines that we're looking at in this problem. Photons of the highest frequency will be emitted in a transition from level N equals something to N equals something. Now, like on the last question, when we talked about emission lines, we talked about how basically the length of the line is related to energy. And this question asks about frequency, which has a relationship to energy. See if you can use this information to figure out which of those possible answers is the correct one. So at this time, I would encourage you to pause the video, work on your question, and when you're ready, you can unpause it. Pause the video now. Okay, I'm going to assume you've worked on this question and you're ready to look at the answer, which is fantastic. All right, highest frequency. All right, we have to go back to the idea of Planck's constant, where E equals h nu and E equals hc over lambda. And highest frequency, which is the new part right here, means highest energy. So if we can find which of those gaps would be the highest energy, we would then that would then correspond to the highest frequency. Frequency and energy are proportional to each other. Now, this y-axis right here, pretty sloppy arrow, is an energy axis. So the bigger the gap we're going to get, the bigger the transition, the bigger the energy, which means the biggest frequency. And as you can probably imagine, if you have an n equals 5 to n equals 1, that's going to be the biggest energy gap you can get. The levels get closer as you get higher in N, but the 5 to 1 should be the biggest transition, and that's going to be your answer, answer E. So the biggest arrow is the biggest gap between the levels, and because it's an energy axis, that means the 5 to 1 would have the highest energy transition. And then because energy and frequency are proportional to each other, highest energy would mean highest frequency. So 5 to 1, highest frequency because it's highest energy, etc., etc. That would also correspond to the smallest wavelength, but we're not really talking about that in this problem. Here's a question that's not hard, but it does take a lot of steps. And the question says, calculate the wavelength in nanometers associated with an energy change of 182.3 kilojoules per mole. Now, in this problem, you have a energy. It's in kilojoules per mole. And you've got to go all the way back to wavelength in nanometers. So you're going to use Avogadro's number, Planck's constant, speed of light, joules to kilojoules, and meters to nanometers in this problem. So see if you can use all this information to calculate which of those is the best answer. I encourage you to pause it. When you're ready, unpause it. We'll talk about the answer. Pause your video now. I'm going to assume that you have tried this problem and you're ready to see how you did. So without further ado, let's check it out. There's lots of equations in here, but here's kind of the idea. Energy equals hc over lambda, all right? And we're after the lambda, the wavelength. But the energy that comes out is usually joules per photon. So what we have to do here is we're going to take kilojoules per mole and turn it into an energy in joules per photon. And when we do that, we're going to get out a wavelength, but it's a wavelength in meters. And from there, we have to turn wavelength in meters into a wavelength in nanometers. So lots of different steps here. And it's all stuff you can do, but it's no problem. So what I would do here first is turn kilojoules per mole into joules per mole by multiplying by 1,000 joules per mole. And I would then take the Avogadro's number, I would divide by Avogadro's number to get the joules per photon. And that's what this number is right here, the 3.027 times 10 to the minus 19th. That is the joules per photon, the energy of the transition. But we're not done yet. We have to still convert that over into wavelength. So wavelength equals hc over the energy. And the number that comes out is this 10 to the minus 7th, answer B. And that's the wavelength in meters. But the wavelength in nanometers, we then have to divide by 10 to the minus 9th in order to get the wavelength in nanometers, 656.3 nanometers. Go through the math, make sure you can do all this. If you do have questions on any of this, be sure to reach out to me. I'm happy to help. If you divide by a power of 10, sometimes it can get tricky if you're not using the EE button. So definitely let me know if you're not getting any of these answers. This question states, what is the observed wavelength for an electron traveling at a speed of 1.20 times 10 to the 8th meters per second? Now, first of all, this is about wavelength, but this isn't like the wavelengths we've been talking about. The wavelengths we've been used previously are for electromagnetic radiation. So E equals h nu equals hc over lambda. Those are for electromagnetic radiation. If you have a particle and a particle with mass, so for example the electron, all right, or protons or baseballs or whatever, you don't use those wavelength equations. What you want to use here is the de Broglie wave equation, so it's a different piece. And like the hint says there, when you use de Broglie's wave equation, you've got to make sure that your grams are in kilograms. So I'm going to erase my little underline there to make sure you've got it. So this would be a good place to stop it, see if you can figure out what the answer is going to be. We'll talk about the answer when you're ready, so stop the video now. Okay, I'm assuming that you've tried this problem and you're ready to check out your answers. So without further ado, let's do it. De Broglie's wave equation, wavelength equals h over mv. H is Planck's constant, 6.626 times 10 to the minus 34. M is the mass in kilograms. And v here is the velocity, the speed. That's the 1.20 times 10 to the 8th button. So if you've done all that, you got to turn the grams into kilograms. So you're going to have 9.109 times 10 to the minus 31 kilograms. But you can see here, here's Planck's constant. Here's the speed mass in kilograms. Here's the velocity. I did turn the wavelength in meters into a wavelength in nanometers. So initially, if you were looking for a 6.06 times 10 to the minus 12, none of those are out there. But however, if you turn the meters into nanometers, which a lot of times people will do, 6.06 times 10 to the minus 3rd nanometers. Femtometers, an FM, answer B, is another metric prefix. A femto is 10 to the minus 15th. It's a very, very, very small unit of length that we haven't used it, so you can probably imagine that's not going to be the right one. But anyway, sometimes just be aware the nanometers are different. Here's a set of quantum numbers, and I'd like you to tell me which of the following is not a valid set of quantum numbers. So use the rules for quantum numbers, see if you can figure out which one it is. This would be a good place to pause the video and work on it, and when you're ready, you can unpause it. Pause your video now. I'm assuming you've tried the video and you're ready to check this problem out. Let's do it. Let's review here fast about the quantum numbers. N, the principal quantum number, starts at 1, goes up in whole numbers like that. It's never negative, never 0, blah, blah, blah. L has an n dependence. L always starts at 0 and it goes up to n minus 1. So for example, on the first one there where n equals 4, L values will go from 0 up to n minus 1, from 0 up to 3. So L values here will be 0, 1, 2, and 3. There's going to be 4 possible L values. M sub L has an L dependence, just like L has an N dependence. And M sub L goes from negative L to 0 to plus L. So M sub L has to be between negative L and plus L. So if you look at A, n equals 4, that's a legit n number. L can't be bigger than n minus 1. So L of 1 is certainly less than L than 3, so that's okay. M sub L depends on L. M sub L has to be somewhere then between negative L and positive L, negative 1 and positive 1. That would be negative 1, 0, and plus 1, and negative 1 is cool. A is okay. B, the second one, n equals 6 is a whole number, no problem. L is less than n minus, less than or equal to n minus 1, so 6 minus 1 is 5, that's okay. M sub L has to be between negative L and positive L, and 0 is between negative 5 and positive 5, and M sub L again of 0 is a legit number. It doesn't mean it's not there or something. B is okay too. On C, n equals 2 is legit, has to be 1, 2, 3, 4, whole number, no problem. But L of 2. Now L can be no bigger than n minus 1. So if n is 2, L has to be 0 or 1. L of 2 is not going to fly. So the problem is C here. L can't be bigger than n minus 1. Now M sub L is okay on C. If you look at D and E, all of those are okay too. But the problem here is that L can't be bigger than n minus 1. So on this problem, C is the difficult problem, the one with the problem in it. For a certain orbital, n equals 3, L equals 1, M sub L equals negative 1. And it says, what type of orbital is this? This is in a question about the NL notation we talked about in Chapter 6, Part 1. See if you can use that information to find the right answer. This would be a good place to pause it. The video, we'll work on it when you're ready by unpausing it. Pause the video now. Okay, I'm assuming you've worked on this question and you're good to go. In the NL notation, the n number literally is 3. So because n equals 3, 3D, 3P, and 3S. Sorry, I said that out of order, but those would all be legit. You wouldn't have 4D or 1F because N of 4 would be 4D, N of 1 would be that one. Okay, so the answer is going to be one of the other ones. And to figure out the letter, we use the SPDF system, and those represent values of L. So 0, 1, 2, 3. L of 1 would be a P, so we would say that this is a 3P system. All right, it's a 3P orbital. If it was 3S, we would have N equals 3, L equals 0. If it was 3D, you would have N equals 3, L equals 2. But because N equals 3, L equals 1, it's 3P. Which of the following orbitals has 2 spherical nodes? And there's 5 possibilities here. Remember from the last one, number of spherical nodes equals N minus L minus 1. So see if you can figure out from this list what that answer is going to be, and we'll talk about it in a minute. So pause the video now, and when you're ready, you can unpause it. We'll check it out. Pause your video now. I'm assuming you've tried it and you want to look at the answer now. So without further ado, let's get into it. So number of spherical nodes equals N minus L minus 1. And you want to have N minus L minus 1 equal to 2. All right. So we're trying to find here an example of where that's the case. So 1S would have N of 1, and remembering SPDF stands for L of 0, 1, 2, and 3. 1S would have L equals 0, so 1 minus 0 minus 1 would be 0. So it's not the first one. That's not going to fly. For B, N equals 2. P means L equals 1. So for that one, you would go N of 2 minus 1 minus 1. That's also 0. That's not going to fly. The next one, N equals 3 for 3D. D means L equals 2. So we go 3 minus 2 minus 1. That one also has 0. That one's not going to do anything. D, 3P, N equals P, 3 equals means L equals 1. So we would go 3 minus 1 minus 1, 1 spherical node, but it doesn't have 2 spherical nodes, so that's not right. So let's open the last one. 4P means N equals 4, P means L equals 1. 4 minus 1 minus 1, that one's going to have 2 spherical nodes. So answer E would be the best way. And notice again how I use the N and L values to find the number of spherical nodes, knowing that SPDF number system obviously is kind of important for this stuff. Cool. Chlorine has an electron configuration, one of the answers shown below, and see if you can figure out by hook or by crook which one of those it is. What we'll do is pause the video now, work on it, and when you're ready you can unpause the video. We'll talk about the answer. Pause the video now. I'm assuming that you've worked on the problem and you want to see how you did, so without further ado, let's go ahead. Chlorine on the periodic table is number 17. It's Cl, all right? And 17 means that in neutral chlorine, you would also have 17 electrons. Now, one way to do these kind of problems is literally just to add the superscripts together and see if they equal 17. So for example, on the one I just did, 1s2, 2s2, 2p5, that would be 2 plus 2 plus 5, 9. 9 is not 17. C is not chlorine. C is actually fluorine when you figure it out. Same thing for the next one, D. If you count up those electrons, there's 18, and 18 is obviously not 17. D could be, for example, argon. Xenon has, I believe, 54 electrons, so that's way, way too much. The last ones and stuff, if you look at them carefully, only the B has the right number of electrons, all right? It has 2 plus 2 plus 6, that's 10, plus 2 plus 5, that would be 17. The top one has 2 plus 2 plus 6, 10 plus 5, that would be 15. Also 3s can't have more than that, so that one's out. The answer here is going to be B. Make sure that you follow electron filling orders, 1s2, 2s2, 2p6, 3s2, and then the remaining 5 electrons go into the 3p. Answer B would be correct. The electron configuration for tin is, and there's 5 possible answers. Now, if tin is Sn on the periodic table, it's number 50. So see if you can use that information to figure out what's going on here, and pause the video, unpause it when you're ready to talk about it. Pause the video now. I'm going to assume that you've worked on this problem and you're ready to look at it and stuff, so let's check it out. Okay, so tin, number 50, is in the P block, all right? And knowing where tin is on the P block can be really helpful. So example of that, boron is a 2p. It's in the second period and the P block. Aluminum, right below it, is the beginning of the 3p block. Likewise, gallium, Ga, would be the beginning of the 4p, and indium, number 49, which is right next to tin, indium would be an example of something in the in the fifth period, 5p, okay? So the outer electrons here for tin are not going to be 4p's, they're going to be 5p's. And you can probably imagine that 50 electrons is certainly a lot less than 118 electrons, so that one is flat out too. So anyway, I'm digressing. My own silly joke sometimes it made me distracted. Anyway, 5p. So 5p1 would be indium, and that means that tin would be 5p2. But you can see the difference between the answers C and D is, do we use krypton or do we use xenon? And it kind of feels like maybe you should use xenon because it's a lot closer to tin than krypton is. But the rule is you always go backwards. Krypton has 36 electrons to it. So if you added 36 to the superscripts that are left, 36 plus 2 of 5s plus 10 for 4d and 2 for 5p, you're going to get 50. Xenon, on the other hand, is 54. That's more than tin's 50 electrons, so it can't be that one. So the answer here is going to be C, all right? And notice there how I used my knowledge of the blocks and the numbers to figure out, what would be the P block. Tin is definitely a 5p system, and if indium was 5p1, then tin would be 5p2. And finally, you have to go backwards for noble gases. You can't go forwards. So it's not going to be xenon. Xenon would have more electrons and stuff than that. It's going to be the krypton. Cool. What element has the following electron configuration? And you can see it has a neon core, a 3s2, 3p4. See if you can use this information to see which of those answers is correct. I recommend pausing the video, working on it. When you're ready, you can unpause it. Pause the video now. I'm assuming you've worked on it. You want to see how you did, which is fantastic. One way to do this is just to add electrons. So neon is 10 on the periodic table. That means 10 electrons, plus 2 for 3s, 12, plus 4 for p's. That's 16 electrons total. So probably here the answer is going to be B, sulfur, because sulfur is number 16 on the periodic table. But you could also find the raw configuration of sulfur. Sulfur is 1s2, 2s2, 2p6, which would get us to the neon core in brackets there, 3s, 3p4. Whatever reason, this answer here is going to be sulfur. Cool. So you can count electrons, you can see where they are in the periodic table, whichever way you want to do to figure out how this stuff all works out. This is a question about electron configuration of ions, specifically an anion. And I'd like you to tell me what's the electron configuration of phosphide, P-3. So this would be a good chance to pause the video, work on it a little bit, unpause it when you're ready to talk about it, see how you did. Pause the video now. I'm assuming you've worked on it and you want to check this question out. When I do these kind of problems, I start with the neutral version of the atom, which in this case would be phosphorus. And phosphorus, neutral phosphorus, is actually listed in this problem. It's answer B. Neutral phosphorus is a neon core 3s2 3p3. It's got 15 electrons. It's 3 into the p block and stuff, so phosphorus is 3p3. But here we have phosphide, so we have to add 3 more electrons to neutral phosphorus to make phosphide. And those extra electrons just go in the lowest empty spots. Like we've talked about, the p blocks can hold up to 6 electrons, so those extra 3 electrons can just go in the 3p area. Phosphide is going to be a neon core 3s2 3p6, the same as neutral phosphorus, but with 3 extra electrons filling it in, same electron configuration as argon. Most of the main group metals and nonmetals will adopt a noble gas electron configuration. So of those 4 possibilities up there, only E neon and A neon 3s2 3p6, which is argon, would be noble gases. Those would be the best places to start, but we figured out, because we're cool, that A is the best answer. All right. In this question, it says, which ion corresponds to the following electron configuration? And notice here what's going on. We got argon, we have 3D, and there's 2, 4, 5, 6, 7. That's a 3D7, and a 4s, which is empty. So this is going to be a positive ion because transition metals lose 4s electrons first before losing any 3Ds, if they're in the 4th period. If there are other ones, then they might lose 5s first or 6s. So see if you can use that information to see which of those ions corresponds to this configuration. This would be a good place to pause the video, unpause it when you're ready to talk about the problem. Pause the video now. I'm assuming you've worked on it and you want to see how you did, so let's check this out. Now, what I would do in this problem is this thing has 3d7. So that's 2 electrons, 4 electrons, 5, 6, 7. Hund's rule says put them all in their own box first, only pair them up when you have to. But the important part is 3d7. So what I would do is I'd try and find what the neutral version of this atom is. And a neutral version would just have a 4s2 filled up. So on my periodic table in front of me, I'm going to start with scantium, Sc, which would be a 3d1. And I'm just going to move right until I get to 3d7. So scandium 3d1, titanium next to it would be 3d2, vanadium 3d3, chromium 3d4, at least in theory, it's one of the freaks of the N+L rule, but I digress. Manganese 3d5, iron 3d6, and lo and behold, cobalt would be 3d7. So if we had neutral cobalt, we would have an argon 4s2, those are always filled in first, 3d7. But this thing has an empty 4s orbital, so it's least going to be a positive 2 charge. So it makes kind of sense that with cobalt plus 2, you'd pull those 4s electrons off and you'd have 3d7 left over. And that's exactly what it is. So this answer is going to be the cobalt plus 2 ion. All right, if you figure out the charges of the other ones, the iron plus 3 would be argon 3d5. The nickel 2 plus would be argon 3d8. The rhodium would have 4d electrons. It's in the next group down. So rhodium would have a 3d10 as well as a filled 4s2 and 4p6 for that matter. That one doesn't count. And lithium plus 1 would be just a 1s2. Lithium doesn't have that many electrons, so that one wouldn't be a good choice here. The answer here is definitely going to be C. Which of the following ions is diamagnetic? And there's 4 possibilities here. Now, diamagnetic ions have just as many ups electrons as down electrons. Paramagnetic ions have at least 1 electron that's up without a down or down without an up. Use this information to see which one, if any of them, are diamagnetic. This is a good place to pause your video. I'll talk about it once you unpause the video, how to answer it. Pause your video now. Okay, I'm assuming that you've worked on this problem and you want to see how you did, so let's check it out. Of all of the ions up there, all right, a lot of them, at least titanium, vanadium, and chromium, have d electrons, all right, and d electrons are spread out through 5d orbitals. So to be perfectly honest, the chances of a transition metal being diamagnetic are not very good. Zinc 2 plus would be an example of a diamagnetic ion, but the other ones, because you lose the 4s electrons first, almost always the transition metals will be paramagnetic. So knowing that, let's talk about magnesium 2 plus. Now magnesium has a neon core with a 3s2 on top of it, and if you take away 2 electrons from that, those are going to be the 3s electrons. Magnesium 2 plus is going to have a neon core, and guess what? All of the noble gases are diamagnetic. So if you have to guess as to which one is a diamagnetic ion, it probably won't be the transition metal lanthanide or actinide. It's not impossible, but it's very, very rare. It's more likely to be a main group metal or non-metal that has lost or gained enough electrons to be like a noble gas. And in this case, that's definitely going to be the magnesium ion. Which of the following is the correct electronic configuration for the nickel 2 ion? All right, so nickel is number 28 on the periodic table, and I'd like you basically to give me the electron configuration for the nickel plus 2 ion. So use your information of this to work on this. This is a good place to pause the video. When you unpause it, I'll talk about the answer. Pause the video now. I'm assuming you've worked on it. Let's see if we can figure out how you did on this one. So when it comes to ions, I usually try and start with the neutral atom first, and then I work my way to whatever the ionic charge is. And nickel, like we said, was number 28. So nickel has an argon core, which I'll try to write right here. And then the next 2 electrons, potassium and calcium, make it a 4s2. And then you start the d electrons. Nickel, if you count from left to right, is a 3d8. So neutral nickel would be argon 4s2 3d8. That would be neutral nickel, okay? But we don't want neutral nickel, we want nickel 2 plus. Nickel Roman numeral 2 means nickel 2 plus, and plus 2 means that you've lost 2 electrons. So the question is, where do the electrons come from? And the official rules are you always take them from highest n first, and if there's a hot tie, then you go to highest n plus L. But here there is certainly no tie. 4 of 4s is n equals 4. And that's bigger than n equals 3 of 3d8. So in this case, the 2 electrons to be lost are the 4s2 electrons. So what's left then with the nickel 2 plus would be argon 3d8. That would be the electron configuration for this ion. Remember, this is really important with transition metals. Highest n comes out first. That usually means the s2 electrons in front, and then the d's, whichever one you're looking at, would be left after that. Tin 2 plus is another possible ion you can do. We talked about neutral tin earlier. See if you can use your information and knowledge of these to find what the correct electron configuration of tin 2 plus would be. And again, this is a good place to pause the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've worked on it. You want to see how you did. So without further ado, let's check this out. All right, we talked about tin earlier. All right, it's a krypton core. All right, krypton is the most recent noble gas. And then after that, we have 5s2, 4d10, 5p2. Okay, so krypton, 5s2, 4d10, 5p2 is the configuration for neutral tin. And again, these configurations are all written a little differently, which you'll see sometimes, but that's what the first one is right there. That would be neutral tin. But we don't want neutral tin. We want tin plus 2. We want neutral tin without 2 electrons. So the question here comes, where do the electrons come from? from. We've got 5s, 4d, and 5p. So again, back to the rules, highest n first, which means we're going to take it from either 5s or 5p, but not 4d, because 4 means n equals 4, 5s and 5p both mean n equals 5. So if you have a tie, like this one, 5s and 5p, you take it from highest n plus l. 5p, p as l equals 1, and 5s, s is l equals 0. So we're going to take them from the 5p before we take them from 5s. Another way to think about it is if you get to the tie, then it literally is last electrons in are first electrons out. 5p electrons were the last ones in. So for all of those reasons, we're going to take the electrons from 5p2. The actual configuration will be B. Krypton 5s2 4d10. So again, on this problem, we knew we had to take away 2 electrons. We didn't know which ones. N equals 5 will come out before n equals 4. And then the 2 electrons will come from 5p first, highest n plus l before 5s. Now, if you're going to make a 10 plus 4 ion, you would take the next 2 electrons from 5s2, because again, n equals 5 comes out before n equals 4. So you can kind of see how this works out. The d electrons are sometimes usually the last ones to come out, or at least it takes more energy to get them out. That would be a better way chemically to think about it. Let's compare these 4 elements with regard to some of the periodic properties. And the question is, which one has the largest atomic radius, i.e. which one has the largest size, which one is biggest? Use your knowledge, work on it. This is a good place to pause if you'd like to, and then when you're ready, unpause it. We'll talk about the answer. Pause your video now. I'm assuming you've worked on it. Let's see how you did. When it comes to size, left and down on the periodic table makes for bigger atoms. So using a periodic table of those 4 elements, look for the one which is more left and down on the periodic table. Carbon is most up and to the right of all of those. And then you can see that boron and aluminum would be next. Boron is more left, aluminum is more left and down, but by far sodium is most to the left and down. So we would argue, just based on the position of the periodic table, sodium is the biggest atom. So again, left and down for atomic size. Left and down also works for ionic size, as long as you compare cations to cations or anions to anions. Cool. This question is basically about the sizes of anions or sizes of cations. And as long as you're using the same kind, anions or cations, you can do this. These are all basically anions. So it says which of the following is expected to have the largest radius? And you don't need to use a table. I'll let you know that right now. See if you can figure out what it is. If you want to pause it, we'll then talk about it when you unpause it. Pause the video now. I'm assuming you've worked on it. You want to check your answer out. Let's get into it. When it comes to ions, it's the same thing as sizes for when it comes to periodic trends, left and down. Now, when it comes to ions, as I said, you can only compare anions to anions, like we're doing here, or cations to cations. You can't compare anions to cations. Anions are always bigger than cations, so it doesn't work. But in this problem, it's okay. You just want the atom which is most left and down. And if you look, argon, chlorine, sulfur, and phosphorus are all there on the 3rd period of the periodic table. And the one that's most left and down, phosphide. All right. Phosphorus has the most electrons and the fewest number of protons, so the electrons tend to wander a little bit more. That's why phosphide here would have the largest radius. So again, as long as you're comparing ion sizes and it's the same kinds of ions, left and down for the largest one. One of these formula and name combinations is not correct. See if you can find out which one it is. This is a great place to pause the video, and when you have your answer, then you can unpause it and we'll talk about the answer. I'm assuming you have this problem figured out and you want to talk about it. So this question is basically about how to name compounds and get names from formulas to names. A lot of these have polyatomic ions, and you know that because the formulas have more than 2 types of atoms. So the first one has calcium, sulfur, and oxygen. That's 3 types of atoms. That means you've got a polyatomic ion. And SO4 minus 2 is the sulfate ion. Calcium is a group 2 or group 2A metal. It wants to be positive 2. So positive 2 calcium with negative 2 sulfate, they go together 1 to 1. Answer A is okay. It's not a problem. Calcium sulfate is CaSO4. Now, the second one, do you have a polyatomic? Well, let's check. Sodium, Na, nitrogen, and oxygen. That's 3 types of atoms or more, so that means, yep, there's going to be a polyatomic ion here too. And the polyatomic ion is NO3, which is nitrate. Nitrate is NO3 negative 1. Sodium in group 1A likes to have a positive 1 charge, so they go together 1 to 1. This is sodium nitrate, and that's a correct formula. Everything's okay on B2. The third one, we have magnesium and we have iodine. 2 types of atoms. Does this have a polyatomic? No. You only have 2 types of atoms, magnesium and iodine. So this does not have a polyatomic. This is a regular kind of compound. So iodide in group 7, 7 minus 8, iodide likes to have negative 1, and there's 2 of them there. Magnesium in positive 2, in group 2A will have a positive 2 charge, so you will need 2 negative ones to balance the magnesium. C is okay. Now, on D, let's count the atoms. Nitrogen, hydrogen, phosphorus, oxygen. 4 types of atoms. You could, and you do, have 2 polyatomic ions here. Ammonium and phosphate. And the NH4 is the ammonium, and the phosphate is PO4. But the problem here is that phosphate has a negative 3 charge, and ammonium, one of the few positive ones, has a positive 1 charge. So if you put a single positive 1 ammonium next to a phosphate, you're not going to get a neutral compound, something without a charge. And that's really important in this section, to have things that are neutral. So ammonium phosphate is not NH4PO4. Ammonium phosphate would have 3 positive 1 ammoniums to balance that phosphate. So the formula would be parentheses NH4 parentheses 3 PO4. That would be the formula for ammonium phosphate. That way the 3 positive 1 ammoniums will balance the negative 3 phosphate, and you'll be good to go. So answer D is obviously the answer. Now, the last one there, just for completion, you do have calcium, chlorine, and oxygen, 3 types of atoms. Yes, you have a polyatomic ion. ClO is the hypochlorite ion, and it has a negative 1 charge. And just like in A, calcium will be positive 2, so you need 2 negative 1 hypochlorites to go along with it. Ca parentheses ClO parentheses 2 is the correct formula. Notice that we did not use parentheses in B, but we did in E, and also for the correct answer there on D. You only use parentheses if there's more than 1 polyatomic ion. If there's only one, like NaNO3 or CaSO4, do not use parentheses. That'll drive chemists, i.e. me, who's grading your assignments, all right, that'll drive all of us crazy. So only use parentheses if there's more than 1 polyatomic ion. Which compound in this list is not ionic? So this question is going to ask you exactly to think about what it means to have an ionic bond, and one of those is definitely not an ionic compound. So at this point, pause the video, and when you're ready, you can unpause it, and we'll talk about the answer. I'm assuming that you have the answer figured out, which is totally cool, and let's see how you did. Ionic compounds are compounds that are held together by positive and negative charges, and it's a very strong type of interaction. So far, we've looked at ionic bonds and covalent bonds. Covalent bonds, the electrons are shared amongst the different atoms. Ionic bonds are much stronger, but covalent bonds are more flexible, and you need those covalent bonds for a lot of things in life. But anyway, to identify an ionic compound, you have to have a metal with a nonmetal, or something that looks like a positive cation with a negative anion. So if you look through this list, lithium is a metal, aluminum, barium, sodium, those are all metals, no problem. And they're all with something negative. So chloride, fluoride, nitrate, -1, and either hydrogen carbonate with a -1 charge, or the carbonate ion, which is CO3 - 2. There's a lot of charges going on. Now, on B, sulfur is not a metal. It's a non-metal. It's above that metalloid line. The oxygen is called oxide because it's more in 2 electrons, and that'll be important to us later. But for right now, because it's a non-metal with a non-metal, answer B is not an ionic bond. In an ionic bond, you have to have a cation and an anion coming together. Sulfur and oxygen, 2 nonmetals, they would use covalent bonds. So again, to identify covalent bonds, you basically want to use nonmetals and nonmetals, while the ionic bonds will usually have metals and nonmetals. Sodium oxalate has the formula Na2C2O4. Based on this information, the formula for iron 3 oxalate is, and there's 5 different possibilities. Now, oxalate is a polyatomic ion. It's a little bit more rare than a lot of the ones we're looking at, but it's the same idea. So using, though, that formula, if you don't know what oxalate is, I think you can figure out what you need to answer the question, to figure out what the formula is for iron 3 oxalate. So try this problem on your own, pause the video, and when you're ready, unpause it, and we'll talk about the answer. Okay, I'm assuming that you've worked on the answer. You're ready to talk about the question. Very cool. Oxalate, as I said, is a polyatomic ion. And if you look at the formula for sodium oxalate, Na2C2O4, the C2O4, that's the oxalate. And sodium is with it. So if you don't know what oxalate is, and that's totally fine, by the way, sodium is a +1 metal. It's group 1A. It's a fixed charge. Sodium's always +1, and there's 2 +1 sodiums there in that formula to balance the C2O4. So C2O4 must have a -2 charge, and oxalate is C2O4 with a -2, if you look it up or if you knew that. So that's going to be important because we need to know what the charge is on oxalate to balance it with the iron 3. And iron Roman numeral 3 means that it's iron +3. So to make the +3 iron and the -2 oxalate balance, you can use crossover or you can use a common denominator, whatever you want. You should find that answer D is the correct answer. Iron +3 times the 2 of them there would give you +6, and 3 -2 oxalates would give you -6, +6, -6. Everybody's happy. You're good to go. So oxalate is -2, and if you knew that, well done. That's awesome. But if you didn't, you can figure it out. Okay, sodium's always +1, so oxalate has to be -2, and then take that -2 oxalate, balance with an iron +3. Good to go. We have 0.25 moles of each of these following elements. Which one has the largest mass? And in terms of mass, what I would do for this problem is I would think about the largest number of grams. You will need a periodic table, I'll tell you that much. See if you can do this problem on your own first, and if you get stuck, no worries. Pause the video, and when you're ready to hear the answer, then unpause it, and we'll talk about it. Okay, At this point, I'm assuming you want to see how you did on your answer to this question, which is fantastic. So in this question, we've got 0.25 moles of each of these elements. Which one has the largest mass? Now, because we're starting with moles and we need to turn it into mass or grams, we need a way to go from moles to grams. And that is going to be the molar mass numbers from the periodic table. So as an example, on A, on my periodic table, if I look at iron number 26, the 55.845 number, that's the molar mass of that compound. So I could take 0.25 moles and multiply it by 55.845, and that would tell which one, how much mass was in 0.25 moles of iron. And I can do the same kind of thing for all those different ones. Now, molar mass, more or less, increases with atomic number. So aluminum, which is number 13, has a smaller molar mass than iron number 26. So we want the atom up here with the largest atomic number, and that's zinc. Zinc has a molar mass, or an atomic number of 30 and a molar mass of 65.38. So if you actually want to see how those numbers work out, those are the actual values. You can see that definitely the zinc here, about 16 grams, that's the mass of zinc from 0.25 moles, and that's larger than the other ones up there. Iron is close, but not quite as big as zinc. So this is a cool question just to make sure you understand what the molar mass means, stuff like that. This is kind of a fun problem. Well, okay, I'm a chemistry nerd instructor, so maybe this is just fun to me, but I'd like you to calculate the average mass of one chromium atom. Now, this at first is a little strange sounding, so I'm going to give you a couple of hints. First of all, chromium on the periodic table is number 24, and you will need the molar mass of chromium to calculate it. So remember, molar mass has units of grams per mole. You're also going to need Avogadro's number in this problem. And remember, Avogadro's is 6.022 times 10 to the 23rd. So for chromium, that would be 6.022 times 10 to the 23rd atoms per mole. And notice there how per mole was in both the molar mass and Avogadro's number. So if you can get rid of the moles, you're going to have grams per atom. Play with this a little bit, see if you can get a good answer. Pause the video, and when you're ready, just unpause it and we'll talk about the answer. Okay, I'm assuming you've tried this problem and you just want to see how you're doing, which is fantastic. So for a question like this, all right, you do need the molar mass of the element, and for chromium, that's about 51.996 grams per mole. You may have a different number on your periodic table, but about that number, okay? That's the grams per mole of chromium. But Avogadro's number says that in a mole of chromium, you're going to have 6.022 times 10 to the 23rd atoms. And in this question, you essentially want units of grams per atom, mass per atom, all right? So if you take thanks for playing. If you take the molar mass, 51.996, and divide it by Avogadro's number, that's going to be how you get this number. And it comes out to be 8.634 times 10 to the minus 23rd grams. So that's answer A. And again, on the bottom right here, you can see how this works. 51.996 comes from the periodic table. That's the grams per mole. You then essentially want to divide by Avogadro's number. The moles on the bottom and the molar mass are canceled by the moles in the top. When you divide by Avogadro's number, you end up with that very, very, very small number of grams per atom. Notice this nomenclature, e to the 23rd. This is another way of writing times 10 to the 23rd. And that's done because computers and sometimes calculators will use e23rd or e10th or something like that. That's totally fine to use your answers that way if you'd like to. Of course, the formal way is to write times 10 superscript minus 23, but you could write this answer as 8.634 e minus 23, and that would be fine. It's just an alternative way to write this, and those are all okay. Okay, that's the end of the review for the Chemistry 221 Exam 1 session. I hope this has been helpful. Now, if you do need more practice on things, I just want to point out that there are some practice problem sets that are both in the companion and online. The practice problem sets have the answers at the end, so you can see how you're doing. Check them out. Concept guides can be very helpful. Concept guides have worked problems from the different chapters, so you can kind of see how it's done. Those are available on both the companion and online. There are chapter guides online, which have lists of all the materials that can help you with, for example, midterm 1 or chapter 1, stuff like that. At the end of the textbook, there are a series of problems where every other answer is given in the back of the book. So try to follow how that works. Not all the answers are in the back of the book, but a lot of them are. So that's another way and stuff to help you get ready. If you have questions on anything, please reach out to me. I'm more than happy to help. You can also talk to the Learning Success Center /Avid Center, located above the library on the Mount Hood Community College campus. They are here to help you as well. All right. Good luck with your midterm. Good luck with your studying, and have a great day.